This is part 2 of the video series on refraction. Right now we're going to focus on the other remaining topics for refraction. So far we've seen a review of the behavior of light in part 1. We saw what refraction means conceptually speaking. We saw how the speed of light and the index of refraction are related to refraction. And now we're really focusing on this part 4 over here, Snell's law conceptually, which actually still does relate to refraction conceptually as well. We're just going to see it in some more detail. And in part 3, we're going to analyze the applications of refraction. But right now we're still in part 2, focusing on number 4, which still implicates number 2. So we're going to focus on a concept called Snell's law. In grade 12, you learn about Snell's law in more detail, mathematically speaking. Right now, we're just going to see what it actually means on a conceptual level. This will involve being able to label and draw a refraction system. So basically just being able to draw a light ray going from one medium to another and showing it bend. And then just being able to briefly define what Snell's law means or understand what Snell's law allows us to figure out. So just to a brief refresher and reminder from last presentation, remember that the index of refraction is a number that represents how slow light travels in a medium compared to space. So if you have an n of 3, that means the light travels 3 times more slowly in that medium compared to space. And you can rearrange this equation over here, the index of refraction equation, to find, let's say, the speed of light in a certain medium other than space. Remember that c is a constant. It's always 3.0 times 10 to the power of 8. And in your learning goals packet, you have 2 videos to help you just study and review the scientific notation that you would have seen in grade 9 science and some of your math courses. Remember that this is the speed of light in a vacuum in space. We studied that light bends when it goes from one medium to another because of changes in the speed of light. So here we have a few terms that we need to know how to define. This diagram illustrates a few different components of refraction. The incident ray that we have over here is the ray coming from the source of light. This first part, the medium where the incident ray is in, that's called the incident medium, and we often represent it by n1, meaning this is the index of refraction of medium 1, where the light ray started off. Now the light ray will go into medium 2, which is the refractory medium, the medium where the light ray is actually refracted. So over here, the ray that bends once it enters the second medium is called the refracted ray, and we represent this second medium using n2, which is index of refraction of medium 2, where light goes into. The angle, just like we saw with plane mirrors, there's a normal. The normal is represented by a dotted line again, and it's perpendicular to the interface between the two media. So it's perpendicular to that surface that separates medium 1 and medium 2. So medium 1, for example, let's say it was air, and medium 2, let's say, for example, was water. Well, the normal would be 90 degrees to the surface of the water because it's in between the air and the water. The angle in between the incident ray and the normal is called the angle of incidence, theta I. The angle between the refracted ray and the normal is called the angle of refraction because it's the refracted ray and the normal making that angle. Okay, so one other thing to point out in this diagram is that you can still see a reflected ray. In reality, even though light is going from air to water, from medium 1 to medium 2, there's always, or there still will be, some reflection occurring. So here we have our original light ray. Some of the energy from the light ray will go into reflection, and some of it will go into refraction. So if you had a detector of light, some light would be detected bouncing off the surface of the water, and some light would be detected entering the water as it bends. Again, the angle in between the reflected ray and the normal is going to be the angle of reflection, theta r, represented with a lowercase r, whereas in angle of refraction, the r is an uppercase r, theta uppercase r. Even though reflection does happen while refraction happens, in this lesson we're going to focus mostly on the incident ray and the refracted ray. So you can actually predict in which direction the light ray will refract or will bend. There's two directions that the light ray can refract. It can refract either away from the normal or towards the normal. So in this situation here we have our theta I. You'll notice that when a light ray goes into the second medium, the angle in between the ray and the normal is larger. So what that means is that the refracted ray moved away from the normal. So here we had a refracted ray bending away from the normal, whereas in this situation over here, we have our angle of incidence, and you'll notice that the angle of refraction is actually smaller. So what this means is that the refracted ray was bending towards the normal, as opposed to away. And so there's a way to predict where the ray will bend. Will it bend towards or away from the normal? And so the trick to remember this is there's two tricks that you can use. There's FST and SFA. So FST, you can remember freaky science teachers, which really means fast to slow towards the normal. So if your light ray travels from a fast medium to a slow medium, it will bend towards the normal. So over here, we have a fast medium. Let's say it was air. And over here, we have a slower medium. Let's say it was water. Because we're going from fast, freaky, to slow, science, the refracted ray bends towards the normal. Teacher. Freaky science teacher. So when you go from a less dense medium to a more optically dense medium, so where the light ray travels slower, the light ray bends towards the normal. In other words, if you have a low index of refraction in the first medium and a higher index of refraction in the second medium, because remember, a higher index of refraction means slower traveling, the light bends towards normal. In the second scenario, SFA, Sarah farts a lot. S means you start off in a slow medium. So that means you have a high index of refraction starting off, high N1. F, fast medium. So a lower N, so a low N2. So this is our fast medium. A lot. Moves away from the normal. So from fast to slow towards normal, that's in this scenario here. From slow to fast, away from the normal. Based on that concept, if you're given information about the two media, you can predict roughly where the light ray will refract to. Will it go towards or away from the normal? I'm not asking for the specific angle, I'm just asking for a rough estimate as to where it would refract. So let's take a look at a sample problem over here. So in the diagrams below, determine which medium has light that travels the fastest and which medium has the highest index of refraction, the top or bottom medium. So we'll do one problem together. What I usually like to do is, if my normal is not drawn in, I draw in my normal in between the two rays, in between the incident ray and the refracted ray, and it has to be 90 degrees to the surface between the media. And I always like to write down my tricks. I like to write down Sarah farts a lot, so SFA. and freaky science teacher, FST. So what I like to do is I like to compare these two angles here. This is my angle of incidence. If you measure that angle and compare it to the angle of refraction, you'll notice that in this scenario here, the angle of refraction is larger. What that means is that this light ray moved away from the normal. So that means we're dealing with our Sarah farts a lot. This was the slow medium. This was the fast medium. So the bottom medium is where light travels the fastest in. That means it has a lower index of refraction. The top mediums are slow one, so it has a higher index of refraction. I'll try diagram B with you and leave diagram C, D, and E for you to attempt yourself. So again, let's take a look. In this case, the incident ray is in the bottom medium. Make sure you look at the direction that the arrow is pointing, right? So the direction in which the arrow is pointing is showing where the light's going to. Here's our angle of incidence. Here's our angle of refraction. You'll notice that the angle of incidence is smaller than the angle of refraction, so that means that the light ray moved away from the normal. So again, we have another Sarah farts a lot situation. This is our slow medium. This is our fast medium. If this is our slow medium, this is our high index of refraction. This is our low index of refraction. Now let's say that a light ray went from medium 1 to medium 2 without refracting. What two possible conclusions could you make? There's two possible conclusions. Think about that. I'll let you attempt the last three diagrams using the same type of analysis that we saw for diagrams A and B. This is another practice problem similar to the one we did on the previous slide. In the diagrams below, determine which medium has light that travels the fastest and which medium has the highest index of refraction, and you would approach it in a similar way. If the normal is not drawn in, make sure that you draw it in between the two rays. So I just want to quickly analyze C. You'll notice our incident ray is over here, and our incident ray is over here, and our so-called refracted ray is over here. You'll also notice that this ray did not bend at all. It came in at an angle. You have an angle of incidence, an angle of refraction. When the light goes from one medium to another, it did not bend away or towards, so we maintained the same angle. So based on that concept, what that means is that chances are the speed of light was maintained, which means that they would have the same index of refraction. So A and B have the same index of refraction, or at least very, 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 very close, that we can't even pick up the bending. But if for there to be no bending at all, it would basically have to be water going through water at the same temperature, because temperature can actually affect the index of refraction of a substance. I do want you to attempt A and B. This over here answers the question I asked in the previous slide about what two conclusions can you make if there's no refraction occurring at all. This is one conclusion, if the light is simply going from the same medium to the same medium, but there's one more conclusion that you can make. Another type of problem you might get is how much did the light refract by? So for example, in this situation, we have an angle of incidence of 45 and an angle of refraction of 32. Now, we went from air to water. Let's see if that makes sense. Air, we know, has an index of refraction of 1.0003. Water is about 1.33. That we know from our table. So what that means is this is our fast medium. This is our slow medium. Did it go towards the normal? It did. So it did. That means this diagram is drawn correctly. How much did it refract by? Well, it didn't refract by 32 degrees. Don't say that. That's the angle of refraction. Look at how close we were to normal initially. We were at 45 degrees. Then we moved to 32 degrees. So we went from 45 degrees to 32. What that means is that the ray moved 45 minus 32 13 degrees. So the ray refracted by 13 degrees. So if it didn't refract, it would have been, I'm not using a ruler, but hopefully you can understand what I'm doing here. If it didn't refract, it would have looked like the arrow I just drew in here. But it did refract by 13 degrees to be 32 degrees away from the normal. So if I asked you how much the light ray refracted by, you would have to do the incident this minus the refracted, the angle of refraction, and that would give you how much it refracted by, 13 degrees. And so you can attempt these two problems over here in a similar fashion. You'll notice that the greater the difference between the index of refraction of the two media, the more refraction occurs. So for example, air is 1. Let's just round down to 1. It's not actually 1 for the index of refraction, but we'll round down to 1. And water is 1.33. It refracted about 13 degrees. Now, diamond is about 2.42 in air. Let's again just estimate it being 1. About 2.42 for diamond. You'll notice it refracted a lot more. Refracted a lot more than the situation over here. So the greater the difference between the two media, the more bending that will occur, because there's a greater change in the speed of light. If the two media were very close in their speeds of light, there'd still be some bending, but just not as much. So again, this concept here is a simple illustration of the idea of how much light bent towards or away from the normal. So in this case here, we have a situation where we are going from slow to fast. That means the light ray moved away from the normal. So this is our angle of refraction. This is how much the light refracted compared to its initial path. So now we're going to do a sample problem where you have to draw in the predicted path for a light ray as it goes from one medium to another. I don't expect you to know the exact angle. There is the formula to figure that out, but I do expect you to be able to predict the direction it would move, so towards or away from the normal. So here are your steps for doing the problem. We're going to start off just by doing these two problems here. You could attempt them yourself initially. So we're dealing with air to water and air to crown glass. So our first media, they're the same. And so if we're going from air to water, we're going from a fast to slow medium. So that's an FST. So I always write my tricks down, FST. That means we're going to go towards the normal. So when you draw this, you need to make sure that your angle of refraction is smaller than your angle of incidence because you went towards the normal. You can attempt the second problem. And again, you need to make sure to clearly indicate that your angle of refraction, in this case here, is smaller than the angle of incidence because, again, you went towards the normal. If you made it larger than the angle of incidence, then that you're showing that it moved away from the normal. So sometimes you won't be given anything and you'll have to draw the entire system. So here's a sample problem. If the angle of incidence in material X is 50 degrees and the angle of refraction in material Y is 40 degrees, which medium does light move faster in? Which material is more optically dense? Answer with a labeled diagram. So my first step is I like to draw the surface. And you would be using a ruler, so you'd make a nice straight surface. I like to draw a normal 90 degrees to that surface. That's my second step. And you'd be using a protractor and ruler, so again, yours would look straighter than mine. Now, the first thing I'm going to do is I'm going to draw in my angle of incidence, or my incident ray using my angle of incidence. You measure the angle of incidence from the normal, and so it would be about 50 degrees. Make sure that the arrow points into the medium because it's going into the new medium. And then you can label your theta I. That's 50 degrees. Your theta R, your angle of refraction, is 40 degrees. So that means you're closer to the normal now. So you need to show that it went 40 degrees from the normal. So it's now 40 degrees from the normal, as opposed to 50 degrees. So we have 40 degrees. So we went towards the normal. Because we went towards normal, you know that's a freaky science teacher scenario. This is our fast medium. This is our slow medium towards the normal. So our fast medium would have the smaller index of refraction. Our slow medium would have the higher index of refraction. Again, use a ruler and a protractor to be as accurate as possible. You should label your diagram, so I would expect you to label your incident ray, your angle of incidence, your angle of refraction. I'd expect you to label your refracted ray, your normal, and also the surface in between the two media. If you know what the materials are, you should write the name of the material. So for example, over here, I'd write material X, and over here, I'd write material Y. And some students would even write NX for index of refraction for X, and NY for index of refraction for Y. This here is just an example of a laser illustrating the concept of refraction. You can see that laser enters this prism here, and this prism is filled with water. So right now we can't. It's hard to see here, but you're following the laser as it's traveling in the water, and then when it leaves the water, you'll notice that it actually left at a different angle, so it bent. And over here, if you draw this in, this would be your normal 90 degrees to that surface of the semicircle there, the flat surface. So we have our angle of incidence there, our angle of refraction here. You'll notice the angle of refraction is larger. And so we went from a slow to fast medium, which makes sense. This is water here. This is air, so it's fast. And that means that we bent away from the normal. Slow to fast there, farts a lot, away from the normal. So to finish off, we're going to see why this bending occurs. Why would a change in the speed of light change the direction of light, make it bend away or towards the normal? And to really understand that, we have to use the wave model of light to explain this concept. The way I like to think about it is like someone who's running towards a post, a light post, for example, and as they're running, they swing their arm out, grab the light post, and when they grab it, it swings them inside. It swings, and they can spin around the light post if they want to. Kind of like this guy here in the video, I'm singing in the rain. He grabs the light post and swings inwards. And that's because, well, the part that grabbed the light post slowed down, and the part that didn't, well, it kept going at a rather fast speed, and that's why he swung around. And that's basically what's happening in the case of refraction. Here we have a light wave. And you'll notice that parts of the wave, when they're going from one medium to another, enter medium 2 before other parts of the wave. And so that causes parts of the wave to change their speed, and other parts of the wave maintain the same speed, which causes the waves to swing. So for example, if these waves here slow down before this part of the wave over here, well, that's going to drag the wave inwards towards the normal. Kind of like this arm here is dragging the rest of his body inwards towards the other side of the lamppost so you can swing around. So it's really because of different parts of the wave entering the media, the second medium, at different times, which causes a change in the speed of different parts of the waves and therefore a dragging of the wave towards or away from the normal. I'll show you this on an animation in the next few slides. So here we have our situation where we have a light ray going from air to water, and I'm representing it as a wave. You'll notice over here that this part of the wave here enters water first and slows down, whereas this part keeps going pretty fast. Because this part slows down, it's like grabbing onto the light post. It's going to swing the entire wave around towards the normal. And then once all the parts of the wave are in the water, then they'll all travel at the same speed, which is why they'll stop refracting once they're actually within the water. So the other situation in which light will not refract, even if you do have two different media, so let's say this was medium A and medium B, and they were actually two different ones, is when the light ray is actually traveling along the normal. In this case, yes, the speed of light will change, but because the light ray is along the normal, all these waves here, all these waves over here, are going to enter the second medium at the same time. So you're not going to have part of the wave enter first and then the other part enter after and cause it to swing around. Rather, all of them are going to enter at the same time. And so they won't have the opportunity to swing from one side to the other. And as a result, you won't see any refraction in that scenario. So the two scenarios we saw where light rays will not refract would be if they're going from the same medium to the same medium, so from A to A, let's just say, or if they're going from one medium to another that are different, but they're traveling along the normal. You should be able to list those two conditions and explain why those two conditions lead to light rays that do not refract. Over here again, because the light rays are entering at an angle, not traveling along the normal, this part of the wave would probably enter first and drag the ray towards the normal. So this is just a summary of what we saw today. We saw that when light goes from one medium to another, it bends because of a change in the speed of light. The medium that our light started off in is called the incident medium, and that's our incident ray. The angle between the normal and the incident ray is the angle of incidence. The light ray that bends away or towards normal is called the refracted ray, and the angle between the refracted ray and the normal is the angle of refraction. And as I mentioned earlier, there's still some reflection happening in this system, so there will be some light rays bouncing off this surface and reflecting, and that will be called the reflected ray, just like we saw last time. And the angle between the reflected ray and the normal is the angle of reflection, and this still follows the law of reflection, which is theta I is equal to theta R. Theta I is not equal to the angle of refraction. There's actually a formula you'll learn in grade 12 that you can use to calculate the specific angle of refraction given what substances you're traveling to and from and the angle of incidence. But for now, you just need to know how to predict the general direction of travel away or towards the normal. So this here is the law that you would use to calculate the angle of refraction. It's called Snell's law. It's written n1 sine theta 1 is equal to n2 sine theta 2. And basically, once you know how to use this, you could figure out your angle of refraction. Angle of reflection is easy to figure out. You just use your law of reflection, but angle of refraction needs the Snell's law. We're not going to use it in grade 10, but I do want you to be aware that there is a formula and a relationship between the angle of incidence, the angle of reflection, the angle of refraction, sorry, and the index of refraction for medium 1 and medium 2. So for homework, you should complete any of the previous homework from part 1 if that's not already done. There are worksheets on refraction that have been provided to you. Make sure you complete those. You can now do the learning goals beyond number 13. And there's a simulation that we will do an activity with later on. I do want you to start exploring with that simulation to aim the angles at the rays at different angles and see how they refract relative to the normal. I want you to explore with this, learn how to become comfortable with this simulation. Just click on the link and you'll see that it'll really improve your understanding of refraction overall.